Okay, and of course, if you take quick notes or whatever, you can always amend them by going to this. And if you miss a class, you can always go to the YouTube channel. I will record these and hopefully post them, preferably the same day. It turns out it's a little harder than I thought it was sometimes, but we'll try that now. So we're going to continue on with Module 1. Okay, so Module 1 was all about structure and bonding, and what we learned about was that we had to, number one, figure out which electrons were the ones that were bonding, and those are the valence electrons. Those are the ones on the outside. Okay, the core electrons don't bond; they just satisfy the charge balance of the nucleus. Okay, so knowing which electrons are the valence electrons is the most important, how many they bring to the party for bonding. And we found out that by looking at the periodic table, we can have those columns suggest how many electrons they have in the system, and that lets them have an easy way for us to know how many electrons we need to put into our Lewis dot structure. And then our Lewis dot structure was very important because, number one, it shows you all of those valence electrons and how they have to fit together around there. And when you have a single line, that's 2 electrons forming a bond between 2 nuclei. And when you have 2 lines, that's 2 bonds between those 2 nuclei. And we can even have 3 bonds between those 2 nuclei. But each of those lines represents 2 electrons. So we need to make sure we remember that. Now, in that case, we have another kind of electron in our Lewis dot structure. We have pairs, lone pairs, and occasionally a single electron all by itself. Those lone pairs are non-bonding electrons. So if they're dots, they're non-bonding. If they're lines, those are bonding. And that's how we have to pay attention to them when we move on to this next section, which is formal charge. Okay, so once you draw all your lines and all of your electrons, and you have as close to an octet for as many of your atoms as possible, now we have to figure out, is there a charge on any one of the nuclei in the system? And so I'm going to go ahead and share my screen now. And I'm going to do it by AirPlay because it seems to work. There we go. Can everybody see my screen now? So it should be just this right here. So this is, instead of presenting in Top Hat, because of the glitchiness that I had last time, I'm going to present from this iPad here. And then we'll see if we can't get more and more into the presenting through Top Hat so I can have those embedded questions. So we're not going to take roll or have embedded questions in this lecture because of the connection issue. Okay, so in the previous slide, we looked at our Lewis dot structure and we followed the 6 different steps. We found out how many electrons were going to be there. We put a less electronegative atom in the middle. We tried to do bonds to connect them, as many as possible. Then we looked for as many ways to fill octets around as needed. So for example, when we filled the octet around this, one, we found out that carbon needed 2 more electrons to fill its octet. And so by just moving these electrons here and creating a double bond, we end up with enough electrons for each of those systems. Remember, we're just trying to make an octet. Sometimes you don't have enough electrons, but when you do have enough electrons, it's good to go ahead and do your structure like that. Now, we need to figure out whether the molecule itself is charged or not, or whether there is a charge on any one or other atoms. Now, this is important because if you draw a Lewis dot structure and you do your formal charge and you have a positive charge on one atom and a negative charge on another atom, I think then you really want to make another bond between them, and then they'll both be neutral. So the idea here is that by checking to see if you have those, by checking to see if any of the atoms are charged and you have opposing charges, you might be able to rearrange your electrons to have a neutral atom. Okay. So how do we figure out what the formal charge is? Well, formal charge is actually calculated for each and every atom. So if you have 3 atoms in your system, you have to do them all. Okay, so let's do, for example, use the Lewis dot structure we had for this compound. O, 1, 2, 3, 4, 5, 6. O, 1, 2, 3, 4, 5, 6. So this is the Lewis dot structure we got from the last slide here. And what we're going to do is we're going to calculate formal charge. So the formal charge of any atom is equal to the number of valence electrons that you had bringing to the party. So nitrogen is a group 5A, which means it brought 5 electrons to bond with. So we have to put 5 here. So this is the number of valence electrons from the neutral element or from the periodic table, okay? Now, the next thing we have to do is subtract the electrons that are either being bonded or non-bonding from that number to figure out what their charge is. But we need to make sure that we take all those bonding and non-bonding electrons together first before we do that. So there's a bracket here. So mathematically, we have to do the non-bonding electrons and the bonding electrons first before we subtract it from our valence electrons. So our non-bonding electrons, so we're going to do a nitrogen here in the beginning, are all the lone pairs we have, lone pair electrons or single electrons. Now in nitrogen here, we have no lone pair electrons, so I get to put 0 here. And then we have plus 1/2 of the bonding electrons. Okay, well now why 1/2? Well, remember, we're sharing those electrons between the two nuclei, so only one of those electrons gets to counterbalance the protons in each nuclei. So we're going to do 1/2 of those bonding electrons. So if we look at here, this bond, and then we have 2 more bonds here. We have a total of 1, 2, 3, 4 bonds, okay? Each of those bonds is 2 electrons, which means we now have 8 electrons in those bonds, okay? But we only get to use half of them, so that turns our number into 4 plus O minus, and then, so that means our formal charge on nitrogen is +1. Okay, so that's important to know. So we know that our formal charge on nitrogen here is +1. Now let's do this calculation again. And I'm just going to leave this +1 over here for nitrogen. And now we're going to do the 2 different types of oxygen. There's the oxygen with the double bond, and then there's the oxygen with the single bond. We're going to do those both. So our formal charge is equal to 6. Remember, oxygen is a group 6, and so therefore it brought 6 electrons to the party, minus. And the one that's double bonded, we're going to do first. So there's 1, 2, 3, 4 non-bonding electrons plus 1/2 of, there's 2 bonds here, so that's a total of 4 electrons. 4 electrons. So 1/2 of 4 is equal to 2. So 2 plus 4 is equal to 6, which means the formal charge on this oxygen here is now 0. Okay, so the non-bonding electrons and the bonded electrons are taken away from the electrons we brought to the party. That equals the same number, and our formal charge is 0. But we do have to do it for each different atom that bonds differently. Notice the other oxygen only bonds once. So we're going to calculate that one too. The single bonded oxygen here, I'm going to do in green. So we have formal charge is equal to, again, 6 because it's in group 6A, minus, and we have 1, 2, 3, 4, 5, 6 electrons in there, the non-bonding electrons, plus 1/2 of the bonding electrons. And there's 2 electrons in that bond, so it's 2. So that's going to give 7 minus 6, which is going to give a formal charge of -1. Okay, so now that means that our nitrogen has a +1 charge, this oxygen has a -1 charge, and this oxygen has a -1 charge. Okay, so what we can do to just make the molecule have a single charge is try to bond it. But the nitrogen in the middle already has 4 bonds. It already has 8 electrons, so we can't do that. So what we have to do now is think of what is the total charge of this species here. The total charge of the species is +1, -1, -1. So this ion is now a -1 molecule. That molecular ion now has a total charge of -1. Okay, does everybody see where the valence electrons come from, the non-bonding electrons, and why we only use half of the bonding electrons? Yeah, good, thumbs up. Okay. The chat is up and working, so you can use that if you want. Okay, so let's do that again, looking at how we can just build this and know that we have really good structural systems. And if we look at this Lewis dot structure, we'll know that our hydrogens always bring one electron to the table and only bond once. So we have a total of, typically our hydrogens have one valence electron and half of those bonding electrons and no lone pairs. So it has a formal charge of 0. When we bring oxygen to the party, it has 4 valence electrons. It has a total of 4 bonds with no lone pairs. So it's going to have a formal charge of 0. And let me erase that so we can see it again. Now we move on to this nitrogen here, okay? And this nitrogen had 5 electrons, and now it has 1, 2, 3, 4 bonds to it. So that's 8 electrons divided by 2, or 1/2 of those. And that means that nitrogen has a formal charge of +1. Okay, but does the molecule have a charge? Let's keep going. So if we look at this upper oxygen here, the one that's double bonded, we ended up with a formal charge of 0 on that because it brought 6 electrons to it. It had 4 non-bonding electrons plus 2 of the total electrons from the shared 2 bonds. But the other oxygen has 3 sets of non-bonding electrons, and therefore it has a formal charge of -1. So the net charge on this compound here is 0 because the plus of the nitrogen balances out with the oxygen. Now, if nitrogen did not have 4 bonds to it, did not already have 8 electrons around it, we might want to try to rearrange those electrons such that we can make that 4th bond to nitrogen. All right, so that's another way that we can use these those formal charges to get to our good Lewis dot structure. Remember, these Lewis dot structures we want to get to at a nice consistent level, because once we have a nice consistent Lewis dot structure, the probability that that compound actually exists in that way is pretty good. And with the number of bonds available to you, you can actually start to see the molecular geometries. Okay, so we can't figure out molecular geometry until we've figured out our good Lewis dot structure first. Okay, so overall, most of the time, the formal charge on each atom is 0, okay? But sometimes that you might be able to rearrange them to minimize that charge, but sometimes you will have a formal charge on there. Negative charges should be held on the more electronegative atom, the one closest to fluorine on the periodic table. The positive charges should be on the less electronegative atoms. Okay, so think carbons and metals and stuff like that. Okay, the structures of 2 atoms with identical formal charges are connected are unlikely to be an accurate representation of the mole. So if you have you've drawn your Lewis dot structure, you've calculated formal charge, and this atom has a +1 and this one has a +1, that is probably not true. If they're both 0, that's fine. But if they both have positive charges, those positive charges want to repel, there's probably something wrong with your Lewis dot structure, and you need to go back and try again. Okay. So, but you can have things, in fact, that do bond more than 4 times, specifically those 3rd row elements like phosphorus and sulfur. When you end up with this separated formal charge of your -1 and a +1, it will use that empty available d orbital to create that 5th bond to phosphorus. Remember, phosphorus and sulfur can go 8, 10, or 12 electrons, but our row 2 elements like copper, nitrogen, and oxygen do not. So just keep that in mind. If you do have a separated charge and a 3rd row element, you can make that more than 4th bond. Okay, so let's look at some really common Lewis dot structures. things that have a formal charge of +1 somewhere on the atom. And remember, we're looking for the formal charge to be on the least electronegative atom. Okay, so in the case of these compounds here, a lot of these positive charges are on carbon. Okay, so we can have a carbon that's only bonded 3 times and is lacking a single electron, so it only has 6 electrons around it, giving it a formal charge of 1, +1. And this is going to be one of our reactive species in the future, and we'll see that again. So we can actually have these nice formal charges on carbon. Another good place to see a formal charge on nitrogen is when there are 4 bonds to it. A 4 bonds to nitrogen typically gives you a nice positive charge. Another way to think about that is nitrogen wants to bond 3 times and have a lone pair. If it shares that lone pair to make a bond, it's going to be down 1 electron and get a +1. Same is true for oxygen. Oxygen wants to bond twice and have 2 lone pairs. However, if you do bond it that 3rd time using that lone pair, it now has 1 electron less in its formal charge, and we end up with these positively charged oxygen species. And on rare occasions, I don't think we actually do that in organic, but you can actually do it for anything with 7 electrons on its outer shell if it bonds twice. So think of fluorine or chlorine. If you ended up bonding it twice, you end up with a positive formal charge. You can also have the correct number of electrons and your formal charge will be 0, but you have unpaired electrons. So when you have this carbon radical, it's actually a neutral species when you calculate out its formal charge. But that makes these valid Lewis dot structures. There's a bunch of different ways to do neutral Lewis dot structures too. Boron's one of the weird ones because it can bond 3 times and just be happy. So we can see that where it'll bond 3 times. In fact, if it bonds again, it typically carries a negative charge. Okay, so boron's one of those weird ones that had 3 electrons in its outer shell and actually doesn't mind maintaining just those 6 electrons. In carbon, whenever you have your 4 bonds to carbon, whether it be single, double, or triple bonds, if there are 4 bonds to carbon, it's typically neutral. Nitrogen is typically neutral when it has 3 bonds and a lone pair. Oxygen will be neutral when it has 2 bonds and 2 lone pairs. And the halogens will be neutral if they're only bonded once. Okay, so those are really common Lewis dot structures. Now, we've already calculated a couple -1 charges in our previous thing, but boron, when it gains an electron to make another bond here, will carry a negative charge. A carbon with a lone pair on it, a carbanion, a carbon anion, that will have a charge on it. So think about 3 bonds to carbon plus a lone pair. In nitrogen, if we have 2 bonds to nitrogen and 2 lone pairs, it will carry a negative charge. Oxygen will carry a negative charge if we just break the 1 bond on the side. In fact, we're going to be using this anion and this anion extensively. Okay, so questions about some common Lewis dot structures and the fact that they can be charged, neutral, or even unpaired electrons in the radical form. Okay, so let's continue on. And now that we have an understanding of why the lines are there and why the lone pairs are there, let's talk about the more common way chemists draw these structures. In fact, the way I will be drawing these structures throughout the rest of the semester is what we call the bond line drawings, okay? Now, there's a couple things. Let's see, how do we put the charge attached to the atom or brackets? Or just pick one? Interesting question. I have a question in the chat here. Where do you put the charge attached to the atom and brackets, or just pick one? If the formal charge is on a specific atom, you assign it to that atom, okay? There will be an opportunity when we talk about resonance that you actually can move that charge around, okay? But if the formal charge was calculated to be on that atom, the charge stays on that atom, okay? Going back to bond line drawings. Bond line drawings are basically a simple way to look at things, but the 3 things you've got to remember are that the lines represent bonds, and typically that's those 2 electrons there, and chemists are lazy, so we don't draw the carbons, okay? But we specifically identify every other atom, okay? Which means that if I drew a line on a piece of on exam and said, okay, what's that? Okay, you're going to go, it's a line. No, it's a line, it's a bond line drawing for a carbon molecule. And so whenever you see a line like that, you're assuming that there's a carbon on one side of there and a carbon on the other side of there, unless it's specifically called out, like here we have an oxygen, a fluorine, or a nitrogen or a hydrogen. Okay. So that's the first rule, is that lines are the bonds between two carbons. Okay. Again, chemists are lazy. So what you also have to assume is if there are no other lines to it, bonds to it, you assume all the other, the total of four, you want total of 4 bonds around carbon, all of the rest of them are hydrogens. So these are assumed that we have, these are hydrogens here. So this line actually represents the compound ethane. And we'll get into nomenclature next chapter, right here. Okay. But the only thing we draw is the line here, because drawing all those hydrogens gets really, really boring and takes a long time. So if we look here, we can imagine that this is a line, and there's a CH3 at the end here. And if we look at this carbon here, it has a total of 3 bonds to it, which means that it needs that 4th bond. There's a hydrogen on that bond. So that's the first thing we need to know about our line drawings, is that they have to be, the lines represent carbon-carbon, and the hydrogens are assumed. Okay, questions? Okay, because we're going to expand on that. So the first thing we want to do when we're doing these, does somebody have a question? No? Okay.
Yes, I did. I'm so sorry, Professor. Could you go over that just one more time? So individual lines are carbon to carbon, and then how many hydrogens are assumed to be attached to those?
Okay, great leading, because I'm gonna explain it in individual steps now. Okay.
Okay.
So in individual steps, all endpoints and all intersections are assumed to be carbon. Okay. So if we look at this, we have at the end here, we assume that to be a carbon. That's a carbon, that's a carbon, but this is a fluorine right here. It's explicitly called out. If it's not explicitly called out, it's a carbon. Okay. So we can redraw our line drawing here to give it a, be more specific, such that we have all these carbons here. Okay, so that's the first thing we want to do. We also want to make sure that when we have the end of a line, we draw a carbon for that. So it's very important to draw that end of the line carbon as well. Okay, so that's the first step. The second step is to attach the hydrogens bound to the carbon atoms. So you want to have a total of 4 bonds to carbon, always. So if the carbon already has 4 bonds on it, like in this case here, you don't have to add any hydrogens. Okay, but if the carbon only has 3 bonds on it, you have to add a hydrogen. If it only has 3 bonds on it, you have to add a hydrogen. If it only has 2 bonds on it, like over here, you have to add 2 hydrogens. Okay, so you fill up your carbon until it has 4 bonds on it with hydrogens. Okay, so and somebody wrote in the chat there, carbon always has 4 bonds, always wants 4 bonds, unless it's charged. That is correct. Okay, so that should have answered your question about how many hydrogens, I believe. So then the next step we do is we add the lone pairs, okay? Because in our line drawings, we don't always explicitly call out the lone pairs, but the lone pairs are important to us when we're making sure that the molecule is arranged correctly. So if we look at all the carbons don't have lone pairs because they have 4 bonds. So we're done there. The oxygen should have 2 lone pairs, and we're going to add them in right here. Right here. And then the nitrogen should have a total of 8 electrons around it. It's bonded 3 times, which means it has a lone pair left, and it has a lone pair. So these are common Lewis dot structures for these elements in their neutral state. Okay. So lines turned into carbons, add hydrogens to all the carbons have 4 bonds, and now add the lone pairs to all the other atoms. This specifically would happen with, oh, we forgot to add some. there are a total of 6 lone pair electrons around that fluorine, or 3 pairs of electrons around the fluorine. Okay. So now, if you have charges, you have to account for those charges. Okay. So for example, when you have a positive charge on carbon, as we saw a few slides up, we know it's missing electrons. So there is no lone pair there. So there's no hydrogen and no lone pair when we have that positive charge on a carbon bonded to 3 other carbons. However, if we had a negative charge on a carbon bonded to 3 other carbons, we have to add the electron to make it neutral, and then the next electron to make it negative. So this one will have a lone pair on it. Okay, so why is this important? Okay, because the shape of our molecule, the shape of our bonds, rests on how many electrons we have, where they are, and whether they're bonding or not. Okay, so does everybody understand how to translate a line drawing into a Lewis dot structure so that we can now look for molecular and electronic shape? What about the F? The F, oh, I added the lone pairs on it. All right, okay, got it. Okay, so that being said, why do we care? Okay, number one, Lewis dot structures tell us a lot about whether we're bonding it correctly, where the electrons were, that we're having these shared electrons in our covalent bonds, but it also tells us about how the molecule is shaped. And to do that, we have what we call valence shell electron pair repulsion theory, meaning that electrons have negative charge. Electrons in an orbital repulse the electrons in the orbitals next to it, okay? Which means they're going to try to spread out as far as possible in 3-dimensional space. And by having a correct Lewis dot structure and knowing a little bit about the valence shell electron pair repulsion theory, we should be able to predict the shape of the molecule and the angles between all the different atoms. Okay, so starting from our two-dimensional Lewis dot structure, we're going to create 3-dimensional models based on this. Okay, and we have to take into account lone pairs. That's why we drew them in our Lewis dot structure, and bonding electrons, because they are each discrete electronic domains. Okay, and those electronic domains are the ones that are repelling each other to spread things out. So let's talk about that. So I'm going to use 2 words here. I'm going to use electronic domains, and then I'm going to use molecular. Okay, so we're going to have electronic geometries, which are where the electrons are. And then we're going to have molecular geometries, which is where the atoms are attached. Okay, so that's the difference between the two. In the case of an electronic domain where we only have 1 or 2 electronic domains, they're going to try to spread it out as far as possible and give us what we call a linear orientation. So imagine just having 2 electron clouds there. All we care about is the electrons, okay? Or we have 2 things bonded to it, and so we have only these sets of electrons bonding, no lone pairs at all. So that means we're going to have a linear structure, and that happens with 1 or 2 electronic domains. If we add a 3rd domain that's going to try to spread it out as far as possible, interestingly enough, even in 3-dimensional space, you get a trigonal planar, a 3-pointed plane that is flat when you have 3. That's as far as they can spread them out. So that's kind of cool that your 3 domains, you go from a linear domain to a 3, then it's still flat. We don't get to our 3rd dimension till we go to tetrahedral. Okay, tetrahedral is when we add 1 more domain to give us 4. The most they can spread out in 3-dimensional space is actually 109.5 degrees. You'll start seeing this. This is the ideal bond angle. Okay, there are things that affect it, so that's what we call the ideal bond angle. If we add another domain to it, now we've gone a little bit crazy. We've gone back to the trigonal planar, but then we have added the linear to it. So we have 3 bonds that are 120 degrees apart in that trigonal planar structure. And then we have an axis coming up and down. And that axis is 90 degrees from that trigonal planar plane. Okay, amazingly enough, that's the best way you can spread those out in 3 dimensions. And then if we had a sixth domain, we're going to see this in phosphorus and sulfur and all the metals. We're going to end up with what we call a octahedral structure. Okay. And the octahedral structure comes from the fact that we have a square planar middle, and then we have our axis. And that means they're all 90 degrees apart. Okay. And that's what we call octahedral. I'm sorry, I forgot to mention the name. This is trigonal bipyramidal, because we have the trigonal that form the plane, but now we have a bond coming up and down. So it's now a pyramid on top and a pyramid on bottom, therefore trigonal bipyramidal. Okay. So these are electron domains. All right. So if we move on and start talking about our electron domains and then figure out how many atoms are actually bonded to this, we can now move to molecular geometry. Okay. So in the case of our linear right here, whether those are lone pairs or whether they're bonded to atoms, it's a linear electron geometry. However, when it's bonded to one or two atoms and has 0 lone pairs, we have the linear molecular geometry. Okay, because we have atoms. Okay, we're not talking about just electrons, we're talking about where the atoms are, and the atoms are arranged in a linear fashion. So that's molecular geometry. Okay, if we had three electron, we have 2 possibilities now. We can actually bond to each of these electronic domains and have 3 atoms on it, and then we end up with a trigonal planar molecular geometry. However, if we only bond with one and have one lone pair, it'll be bent. Okay? And technically, you could have just a linear one with 2 lone pairs here, but that doesn't really exist very often. So, all right. Now let's go to that fourth. Remember, that fourth is that first thing that's 3-dimensional, and now we can actually get some really interesting 3-dimensional structures out of that, depending on how many atoms we're bonding to. If we bond all 4 of the systems, we go from a tetrahedral electronic geometry to a tetrahedral molecular geometry. Okay, so all of those electron domains are spread out evenly. Okay, but if we have one lone pair and only 3 atoms bonded to it, we end up with this thing right here. Notice it's not flat, it's like a little pyramid. So we call that a trigonal pyramidal, okay? And that lone pair on top takes up space, okay? Now, this is why water is bent and not a linear molecule, because it has 4 electronic domains, making it tetrahedral, but it has 2 lone pairs and only 2 bonds to atoms. Okay, when it has 2 lone pairs and 2 bonds to atoms, that gives us a bent molecular geometry. Okay, so having those lone pairs there is important to the molecular structure of our system. Okay, and we can extend that up to the 5- and 6-membered systems. So we can bond them all and have our trigonal bipyramidal right here. If we lose one bond, okay, it's going to try to be in the most spread out area. And so it actually is the bond on one of these tetrahedrals that are 120 degrees apart. And it actually looks now like a sawhorse. If you put this part on the ground, it would teeter back and forth. Okay. So, but it's losing, it's those lone pairs are on that, the orbitals that are most spread out, which are on the tetrahedral plane. Again, if we lose 2, we end up with a T-shaped molecule here. And the lone pairs are going to be in that trigonal planar part of that structure. And if we lose another bond and we have 3 lone pairs, we end up with that linear molecule. So it's very interesting that it would lose the trigonal planars all first to give us those 3 unique shapes in our molecular geometry. When we go on to 6, right here, we have octahedrals when all 6 are there. And again, just like we did in the trigonal bipyramidal, we lose it on the square planar side. And so what we end up with is we get 4 equal and then this, and we end up with what we call square pyramidal. So you can imagine that square is the base and then the pyramid comes out on the top. If we lose another one, we're actually going to lose it opposite the other one, the first lone pair, and we're going to end up with what we call square planar. When we lose another one, we get to a T-shape again, and lose the last one, again, we end up with linear. Okay. So make sure you know the difference between electronic geometry and molecular geometry. And it all goes back to your correct Lewis dot structure. How, when will it lose a pair? I didn't mean lose a pair. I just meant lose a, when you take away a bond and still have those electronic areas, that becomes the lone pair. I'm sorry, I misspoke. Okay. All right. So that's kind of interesting then, because if our theoretical 4 electronic zones in space were to be bonded to 4 things to carbon, we would expect there to be a 105-degree angle, okay? Because all of these are exactly the same, so they're the same size, they're the same shape, so all those angles would be 109.5 degrees. And that's true. It actually turns out that that's how it does, okay? But that is kind of weird because we don't really have 4 equal orbitals, right, that are in carbon. We have 2 s electrons, 2 p electrons, and an empty p. How does that work out? Why can we get these evenly out? So that's going to bring us to a new thing that says, okay, maybe to be able to get these symmetrical shapes, maybe we need to start blending or hybridizing our orbitals so that they look more equivalent. And so that's bringing us hybrid orbital theory. And so instead of having it bond to one of the p's, and then the empty p, we're actually going to do something a little different. Okay. So because we have this, okay, that's the same slide. If we tried to do that with carbon, the way we saw the electrons filling the orbitals, we're going to put 2 electrons in the s orbital first, right here, and then we're going to have 2 electrons left in the 2p, a total of 4 valence electrons. If we tried to bond that, we would try to put 1 hydrogen in one of the p orbitals, 1 hydrogen in another p orbital, 1 hydrogen in that third p orbital, and then the s would be kind of sticking out somewhere in the middle because it's spherical, right? Notice that we would have a 90 degree, a 90 degree, and a 90 degree here, and then this would be sticking off wherever else. But that's not what we see. So that means that we can't just be taking these filled from the bottom orbitals up and just start bonding to them. Something else had to happen, okay? So what's happening is we're gonna blend the 2 different types of energy level 2 orbitals together to make them more symmetrical. Okay, so when we started with our system to make, okay, I gotta correct that slide. There is not a 3rd electron here. We have 4 valence electrons in our outer shell here. We have 1, 2, 3, 4. So we have 4 valence electrons in our ground state. And again, that would give us that unsymmetrical bonding that we do not see. So what is happening? Well, what we're going to do is we're going to raise the energy of the s up a little bit and lower the energy of the p a little bit and make 4 equivalent orbitals. Okay? If we do that, if we share the different orbitals together, we now end up with 4 equal orbitals, which gives us 4 equal electronic domains, which will give us 4 equal bonds to give us that symmetrical bonding structure we see. Okay, so just from the fact that we can analyze our chemicals and know that they have that 109.5 degrees tells us this must be blending our orbitals together to make them equal. So what does this mean? Okay, so well, if we look at the shape of our s's and p's, just as they are, the s is of course spherical, and of course the one s is way down here and it's completely covered by the other s, so we're not worried about that. That's the one s. Okay, now when we looked at the p's, we saw that there was one pair of lobes on the x-axis, 1 pair of lobes on the y-axis, and 1 pair of lobes on the z-axis. Okay, so and notice those 2 different sides of the lobes are equal in size. Okay, now when we start blending our s and p together, what's going to happen is the s is going to be incorporated into one side of that p orbital. So you're going to have a slightly larger lobe on one side than the other. So when we hybridize it, we get to a large lobe and then a small lobe, and a large lobe and a small lobe and a large lobe and a small lobe, etc. And when we take those together, imagine taking 4 balloons and trying to tie them in the middle, they're going to spread out into this tetrahedral shape. Note that the small lobes actually fit in between in the spaces that are in between those. So we're not losing those small lobes. They do exist, but the largest portion of electron density is now in these large lobes equally spaced around the central atom. Okay. So that happens, that's the shape we get when we take one of the s orbital and 3 p orbitals together. Okay, we call that sp3 hybridization. So if you imagine there's a 1 here, that's a total of 4 equal orbitals. Okay, so sp3 gives you 4 equal orbitals, gets you that tetrahedral shape. All right, well, do you have to blend them all together? What if you already had 2 electrons in your p, one of your p's? Well, we can do that. So let's say you don't take all 3, okay? Let's say you only take 2 of these, 2 of these p's and the s, and those, notice that we're losing energy in p and gaining energy in s, and left 1 p unattached, okay? So that's going to give us s and 2 p's for a total of 3 orbitals that are equal, okay? So that's 3 sp2 hybridized orbitals that'll have 3 equal things. Okay, wait a minute. We have 3 equal electronic zones now. What electronic shape do we have now? We're no longer tetrahedral. We have 3 equivalent electronic shapes, which means we're going to be trigonal planar. These are going to give us a trigonal planar. And then that we're going to have this unreacted p that's just going to be somewhere else. Okay. So what does that look like? Okay, when we take that and we do that, the 3 equivalent ones are going to give us that that trigonal planar geometry. So if we look at this hydrogen here and this hydrogen here, and then this carbon bonded to here, this is our trigonal plane. Okay, so that's the hybridized orbitals. Okay, now because we have 3 of those hybridized orbitals, we can form 3 of those sigma bonds. Okay, but we have a p left over. Okay, that p is now, because this is trigonal planar, we now can add a electronic zone above and below that plane. Okay, I'm exaggerating the size here so you can see it. You have that plane above and below that plane. Okay, so because that orbital is above and below that plane, it cannot directly bond to an atom next to it. Okay, a sigma bond is a direct bond between 2 atoms. Okay, so directly in between the 2 nuclei. Notice all the electron densities between the 2 nuclei. Okay. Now, when you have 2 adjacent p's, so you have a p on this orbital on this side too, because this carbon was sp3 hybridized as well. Now you have an opportunity to do what's called a sideways overlap. And when you do that, so you have 1 electron in this orbital and 1 electron in this orbital. And when we share, we're going to share some of the electron density on the top of the system, but some of that electron density shared on the bottom too, because those 2 lobes are equal. And so we have what we call an overlapping bond. This overlapping bond is what we call a pi bond, because it's above and below a sigma bond. Okay, so we have sp2, so that's trigonal planar, which means the angle between all of our atoms here is going to be about 120 degrees. And those p orbitals are going to be in that z-axis sticking above and below that plane. And when they overlap, they can create that pi bond. So write that out. Sigma is a direct bond between 2 nuclei. A pi bond is an overlapping bond above and below a sigma bond. Okay, so pi is overlap. Okay, so that's an important thing to know. But that also tells us why we went from having 4 single bonds, 4 sigma bonds, to something that has 3 sigma bonds and a pi bond. And so we've gone from just single bonds between two carbons to double bonds between carbons. And it all happens because of the hybridization. Okay, so do we got that? sp3, 3sp3, yes. There's a question about there's 3 sp2 orbitals because there are a total of 3 electrons available, yes. So we can do that again, where all we do is share one of the p orbitals and spread the electrons out. And so our s comes up a little bit. One of our p's comes down quite a bit, and we end up with 2 equal orbitals. And then we have 2 untouched p's. P orbitals, okay? Which means these are hybridized, and then these have that double lobing system. So they look a little different. So if we look at that, the hybridized orbitals are the ones that can do pi bonding, okay? So we have 2 electronic zones in our hybridized orbital, the s and the p, which means that s and p is going to create the, oops, let me change to red here, the bond between the hydrogen and the carbon, and the bond between the carbon and the carbon, and then the bond between the carbon and the hydrogen. Okay, that's used up 2 of those orbitals. We still have 2 left. We have 2 p's, okay? So just like before, our p orbitals are on the x-axis, the y-axis, and the z-axis. So one of the p orbitals that's not hybridized is on, let's call that the y-axis, right here. And because they're on the same axis, those 2 can actually overlap with each other. Notice that you cannot overlap something on a y-axis with something in an x-axis. They're in the wrong orientation. They will not work. But if you had 2 adjacent unhybridized p's that are in the same axis, they can overlap, forming a pi bond. Now, we also have, let's call this the z-axis here. We have 2 unhybridized p's in our z-axis, and they can overlap to form another pi bond. Okay, so hybridized orbitals only form sigma bonds. Pi bonds are only formed by unhybridized p's. And in this case, we have 2 unhybridized p's, which means we're going to have 2 pi bonds. Okay, and one's going to be in the plane with the sigma bond, and one's going to be above and below that plane. So do we see that moving from the idea that we had 2 electrons on our s and 1 in each of these p's and an empty p really wouldn't bond very well, but we can start blending those together now, and we can blend them together in different ways. And as long as we can go, 1p, 2p, or 3 p's. Anyone else? Oh, frozen. All right, let's see. Okay. It's back now? All right. Okay.
I have a question.
Yes.
The overlap between the z-axes, what is that called?
Okay, so if we are talking about these right here, okay, so if we have an unhybridized p orbital and they're both in the same axis, those can overlap to give us a pi orbital, okay? If we have hybridized orbitals, those are going to give us those direct orbitals, and those are those direct bonds, and those are sigma, okay? Okay, let's move on a little bit and email me about the molecular geometry thing and we'll talk. Okay, so that being said, I have a little summary slide here. And the idea is that when we have the ground state here, that ground state would not give rise to the bonding we see in our structure, would not give rise to the molecular geometry in the structure we see. So that leads us to the idea that maybe we have a certain amount of hybridization between the S and the P in the same energy level. In this case, it's the principal energy level 2. And when we do that, we have our core electrons untouched, and each of these is 1/4 S and 3/4 P, because we're spreading that S orbital out over 3 different P orbitals. So of those 4 orbitals, a quarter of each of those hybrid orbitals is S character, and the rest of it is P character. When we only blend the s over 2 p orbitals, it now comes up a third character. Okay. Now, I'm saying this because that s character gives rise to different, slightly different shapes in those orbitals. Okay, and we'll see that in the next slide. So the hybridized orbitals can form sigma bonds, and the unhybridized orbital p is above and below that sigma bond to give us our first pi bond. And if we do it again, where we only have 2 in here, it's half s and half p. So it's shaped a little bit differently. And then we have 2 p's available to pi bond the first axis and then pi bond the second axis for a total of 2 pi bonds. Okay, so okay, I'm back, I'm still good. All right, so that's telling us, number one, molecular geometry is controlled by how many things are bonded to something, and the fact that the way carbon bonds to give us these 3 different types of molecular geometries tells us that we have hybridization of them. Okay, so I'm going to get to the the percent character here, on the next slide. Okay, so I said, okay, no, I'm not. All right, let me explain this S and P character. So when you have only, you have 1 s orbital spread out over the total of 4 hybrid orbitals, that means each of those hybrid orbitals has 1/4 of the s orbital, and each of the other hybrid orbitals is 2/3 the p orbital. When we only spread that s orbital out over 2 other p orbitals to make 3, it's only 1/3. It's spread out over evenly over those 3 orbitals, so it's 1/3 s character. And when we have s only shared with 1 p orbital, that means we're going to have 2 orbitals. So we have, it's half s and half p because of that. Okay. Just the general, please remember the general idea of where the bond angles are. They change based on other groups that are attached to them. But the idea is that those bond angles are related to the molecular geometries we found from our valence electron pair repulsion theory. Okay, let's see. Are we over time? Is it 1:20, right? Okay, let me finish one slide here. No, we go till 2. Sorry, good. All right. So, but the cool thing is that nitrogen and oxygen also do this hybridization to give us our system. And that actually shows us why the nitrogen would give us that pyramidal and where the lone pair would be. When we hybridize nitrogen in its ground state, we have a total of 5 valence electrons, okay? But when we go into that hybridized state where we have 4 sp3s, that means we have 3 single electrons available to bond, but we have a lone pair, which is going to give us this trigonal pyramidal structure with the lone pair being in by itself on the other side. Now, if we hybridize just 2 of those p's, we would end up with something looking like this. Again, if it's an sp2 hybridized, that means it's going to have a bond for each unpaired electrons, a lone pair for the paired electrons, and then a double bond or a pi bond with that unhybridized p. Same goes for if we only go for the sp, we'll have 2 lower orbitals, 2 p orbitals to give us 2 pi bonds. But notice that we're going to have a lone pair sticking out on our system and 1 bond to some other atom that's a sigma bond, and then 2 bonds that are pi bonds. Uh-oh. Lost my Diet Coke. Okay, questions on that? So all of the second row elements, nitrogen, oxygen, carbon, all do this. Okay. Okay, so let's summarize our molecular structure associated with the hybridization. In hybridization, sp the sigma bonds are going to be linear, always, the 180 degrees apart. In an sp2 hybridized, if you have 3 bonds to it, having all 3 of those equal electron zones bonded to it, then you'll end up with trigonal planar. However, if you only have it bonded to 2 and have a lone pair, now you have bent. Okay. So we're saying that the hybridization type changes the molecular shape. Now, the sp3 hybridized gives you the most variety. If you have 4 things bonded to it, here it says ligands, imagine bonded to another atom, and no lone pairs, you're going to go back to your tetrahedral shape. If you have 3 things bonded and 1 lone pair, that's going to give you your trigonal pyramidal. And if you have 2 bonds and 2 lone pairs, like in water, it's going to be bent. Okay. So now this is tying together electronics, Lewis dot structures, electronic structures, molecular structure, and hybridization, all tying together to get to this point where we can predict the shape and structure of our compounds just from our Lewis dot structure. Okay. So like I said, ligand is really just something that's bonded to. So in this case, we're going to say bonded to another atom. All right. Questions on that? So let's continue on and see if we can't relate that to us. Okay. So the Lewis dot structure gives us the basic shape of the molecule. The electron pair repulsion tells us what 3-dimensional shape it'll have, right? And the difference in electronegativity told us whether we had a polar bond or a non-polar covalent bond. Okay, so between polar and non-polar bonds and the number of electronic zones and the number of connections to atoms, we end up with a really good foundation for looking at intermolecular forces in between compounds. What this means is when this atom starts coming up to this atom here, are they being pulled apart, being pushed together? What's happening? And so we can look at these macroscopic, meaning things you can measure, physical properties like boiling point and melting point and solubility, and look at the kind of interactions that have to be there between these atoms, these molecules. It's between molecules. So these intermolecular forces are either an attraction or a repulsion of those electron-rich or electron-poor regions. Now, what do I mean by that? Remember, we had bonds that were polar, meaning that one side's going to have more of the electrons than the other. So you're going to have a slightly positive side and a slightly negative side, and this can lead to an interaction between them. Okay. Now, the strength of the intermolecular forces depends on the magnitude of the partial charges, the distance, the surface area. All of these take into account the different type of interactions we have between molecules. Okay, so the first thing I want to talk about is we've talked about bond polarity, but now we're going to talk about molecular polarity. And molecular polarity is basically adding up all of the bonds and seeing in what direction the electrons are being pulled. So in the case of methane right here, we have hydrogen right here, which is a 2.2, carbon, which is a 2.5 right here. And so that we call that a non-polar covalent bond. Now, the carbon is slightly more electronegative, so it's pulling a little bit of electron density here. But if we added all those up, they all cancel each other out because they're all in opposing directions. So we're calling this molecule non-polar because it has non-polar bonds, and all those bonds point in the basically cancel each other out because they're opposing directions. Now, let's change 2 of those atoms. Change out these 2 hydrogens for chlorine. Now, chlorine is the more electronegative atom. So we're going to have some of the electrons being pulled by the carbon from those hydrogens, making this a little bit positive up here. But we have a net direction in this, a net direction from the hydrogens right here is kind of in this direction here. That's where the electrons are being pulled. Now let's look at the carbon and chlorine here. Chlorine is more electronegative, so it's going to pull some of electron density that way and electron density that way. So the net pull of electron density is also in this direction. So if we add the blue line and the red line together, that gives us a net direction of electrons being pulled, okay? Okay, so if we have a net direction of where the electrons are being pulled, we call that compound, we say that compound is polar and it has a dipole moment, okay? A dipole moment, meaning you have two poles. You have a positive side and a negative side. And you have a net direction in which the electrons are being pulled, okay? Now, in the case of methane over here, they all cancel out, so there is no dipole. In the molecule, each individual bond canceled each other out, so you have a net thing. So that's how we have molecular polarity, and it's all derived from the net, the adding it together of all the bond polarities. Okay, so now that we have those bond polarities, actually I want to start with this one here. What we can think about it is the more electronegative an atom is, the more likely it is to pull electrons toward it. So in the case of this water molecule here, right here, oxygen's more electronegative, so it's going to pull some electron density that way and that way, right there, making this side of the molecule more negative. Not a full negative charge, just more negative than the other side of the molecule. And we call that partially negative. And in this case, we can calculate that out to be almost a full negative charge, but not quite. Now, the other side, that makes this side and this side, having some of its electron pulled away, now partially positive. And so we look here, we can actually calculate those out. So in this description here, we're seeing that one side of the molecule has a partial negative charge and one side of the molecule has a partial positive charge. And this is typically denoted by the fact that we have a red zone on one side of the molecule, which is typically the negative side of the molecule. And the blue zones tend to be the more electropositive sides of the molecule. The green is right in the middle. It's kind of the nonpolar zone of it, okay? So this can change based on how strongly or how much electron density can be pulled away. So if we extend this out, and instead of just having hydrogens, actually add some carbons here, the oxygen cannot pull away as much electron density from the carbon and those three hydrogens, and therefore it's less partially negative. So we have a partially negative side of this, delta negative, and we have a partially positive side of it, but it's not as polar as the case of water, okay? So when we have this, that means this has a positive side and a negative side, so this means it has a net dipole. So it has a direction of electron pull. This has a net dipole, and we can measure the strength of those net dipoles, okay? So if we measure the strength of that net dipole, we call that a dipole moment. And just by looking at a few structures here, we can see that the dipole moment can correlate to the electronic structure based on the shape of the molecule. So for example, if we drew in our lone pairs right here, we would see that this is a bent molecule and we have a dipole moment of 2.8, okay? Relative, that's one of the more polar things we have on this table. If we have something like this, we have a whole bunch of electrons here and oxygen is more electronegative. So it's actually pulling electrons in this direction, giving this side a partially positive side, and this is our negative side, and it has a significant dipole, okay? Just by having one polar bond, so there's only one polar, only the chlorine is pulling electron density from that carbon, we get a significant dipole. Water has those two dipole individual polar bonds. Ethanol is now less than that of methanol, okay? So the fact that we have more place to spread this partially positive charge on this side, meaning it's decreasing the intensity of the dipole because we're spreading that charge out. Look at a couple more. Ammonia is less electronegative than oxygen is. So it's pulling less on those hydrogens, and therefore it has a lower dipole. Here we're pulling a whole bunch of stuff we're spreading that positive charge out over a huge amount of area. So our dipole drops. Here we have two that are starting to point in slightly opposite directions. Our dipole drops again. And by the time we get to completely symmetrical bond systems, our dipole drops to 0. Because geometrically, they all cancel out. And notice here, even though we have 4 very polar bonds, geometrically, they all cancel out. So we also have 0 dipole. Okay, so do we see what polarity is? And do we see that the molecular, the actual bond polarity controls the molecular polarity? Okay, so let's take that into an extension. So now that we have molecules that have a partially positive side and partially negative side, that's going to change how they interact with each other. Okay. So let's talk about specific intramolecular forces. Okay, so when molecules come together, when different atoms come together, we have 5 typical things we can do in organic chemistry. The first time is ion-ion. Think sodium chloride. These tend to be very strong. It's a full negative charge and a full positive charge. We have ion dipole, where we have a full positive or negative charge and something that has a dipole. Half of it's positive, half it's a negative. So it's going to orient itself kind of interestingly, one way or the other. The next thing we have is hydrogen bonding. When you have hydrogen on an oxygen or a nitrogen, it can start being shared with the lone pairs on those adjacent nitrogens or oxygens. And that gives rise to our third most intense type of bonding, hydrogen bonding. Now, if you just have this side, this molecule has a partially positive side, partially negative side, and this one has a partially positive, partially negative. When they come together, we're going to have a dipole-dipole interaction, but we have to be careful on how we line those up. And the last thing we have, which is the weakest thing, is an induced dipole, induced dipole. This happens when we have something that's already nonpolar, and it's just trying to find some way to interact with its neighbor. And I'll go over each of these. Okay. So obviously the strongest ones are ion forces, because sodium ion, chloride ion, they're just going to bond together just from the true electrostatic difference between them. Okay. And we can then also do the same thing with an ion and dissolve it in a solvent like water, because the ion is being counterbalanced by the partially charged side of the water. So this is our dipole, this is our negative side here, and it's going to be pointing toward the sodium here. Now, that's not a full negative charge. So what we typically do is we put a whole bunch of these around here, and they're all pointing that same direction. The negative side of the molecule is facing toward the ion, and the positive side of the molecule is facing into the solution. And because you have multiple atoms around here, multiple molecules around here, it's sharing that positive charge of sodium between all of those different compounds. Okay, so this gives rise, that's why we have a lot of things like a lot of salts dissolve in water very well, because of ion dipole forces. So the next thing we have is hydrogen bonding. This is typically between a hydrogen bonded to an oxygen or a nitrogen and an adjacent lone pair of an oxygen or a nitrogen. Okay, so what we can think about that is, in this case here, we have 2 water molecules. Okay, and we have a lone pair sticking out here and here. We have a lone pair sticking out here and here. And so that is the negative side of the molecule. And this is the positive side, partially positive side of the molecule here. What can happen is that this hydrogen can actually start to share a little bit of the electron density of that lone pair with an adjacent molecule. When it shares a little bit of that, it gets fairly close. It's not making a full bond, it's just associating with it. And that means that this is a specifically good bond, but specifically easy to form bond, but it's a very dynamic bond because it's not a true sigma bond, it's a hydrogen bond. So it'll be kind of, hydrogen can bond to anything with lots of electrons, but we typically find that in the hydrogen, nitrogen, oxygen, but it does do with fluorine as well. Okay. The next thing we have, and the amount that it affects the properties changes based on how many available things you have to hydrogen bond. So in this case here, we have 2 hydrogens available for hydrogen bonding, and we have a total of 4 electronic zones available for hydrogen bonding. So it has 6 potential hydrogen bonds. If we take one of those hydrogens away and turn it into here, we now only have 5 things, 4 lone pairs and 1 hydrogen. And if we take those hydrogens on oxygen and nitrogen away, we lose all of our hydrogen bonding, and it drops the boiling point. In this case, the boiling point. So hydrogen bonding is actually raising the boiling point of our system because of its availability. Dropping it down to half, a fewer number of hydrogen bonds available lowers the boiling point, and having no boiling points would lower it even more. Notice the molecular weight stayed the same, so it's not about the molecular weight, which also controls our thing, but it's about the hydrogen bond. Okay, we're right here at 1:40, and so I'm going to go ahead and stop. I'm going to post here, I'm going to pick up here, and then we're also going to continue on with Module 2 nomenclature on Wednesday. Okay, SI sessions you should be getting emails from your SI leader. Sheila, the survey closed Friday night, I think, or Saturday morning, and so she should be getting those out to you today. I'm sorry, this week, to assign you to your SI sessions. Okay. Sheila, are you on to answer that better? So yeah, look for an email from Sheila about SI sessions. There might also be something posted on Canvas. I'll ask Sheila to post something.
Oh no. It should have been in the session on the survey.
Okay. I'm sorry. Marcus is our SI, not Sheila. Sorry.
Yeah, that's your other class. My bad. Yeah, but I'm gonna have a flyer out soon with all the SI sessions posted and the Zoom links on there. It'll be out by the end of this week. So then I'll send that out to y'all. But they have started. I did 2 sessions already. I had one yesterday and one on Monday. The survey just closed, so the communication between me and with my bosses and stuff haven't done that yet. So I'll let you guys know as soon as possible.
So they have, Mark, can you also post your current schedule on the Canvas site under announcements, please?
So when I make the flyer, it's gonna have everything on there. Okay. But they have the on the survey. It had all the times and stuff though.
Okay. So yeah, they started, and go ahead and look for that flyer when it comes out this week.
Okay. Yeah.
All right, I'm gonna stop.
Like y'all can email me if y'all have any questions.
And I'm gonna stop.